In this lesson, we are going to start talking about vectors. To fully understand vectors, we have to distinguish between two types of qualities here for any physical object. There are qualities that they don't need any type of direction. Just the magnitude is enough to specify that quality. For instance, when we talk about numbers, when I say, let's say 3 doesn't need any direction. By itself, 3 defines a quality of a number. Or a temperature, something like -5 degrees Celsius. Or another quality we can talk about is the area. For instance, I say the area is 14 square centimeter. But there are other qualities which they need direction too. For instance, the gravitational pull has the magnitude and also direction, which is going to be downward. Also, when you are flying a plane, you need the speed and also the direction to fully specify the quality of that plane. We define a scalar to be a quantity which describes magnitude or size only, with or without any units. It doesn't include any direction. On the other side, we define a vector to be a quantity which has both direction and magnitude. For instance, when we talk about force, which we define as, let's say, F, with the vector on top, it needs the magnitude and also the direction. For instance, we say that the force is 10 Newton downward, or 35 Newton to the left. Another example is velocity. For instance, we say velocity is 10 meters per second upward. Or we say velocity is 80 kilometers per second or per hour toward west. As the first example, we are supposed to state whether each of the following statements is an example of a vector or scalar quantity. The first question is a car traveling at 50 kilometers to the east. It is obvious that we do have the magnitude, 50 kilometers, and also the direction. So this represents a vector. The second question says a child pulling a wagon with a force of 100 Newton at 30 degrees to the horizontal. Again, you do have magnitude, 100 Newton, and also the direction, 30 degrees to the horizontal. So this represents a vector again. The next one is a man's mass of 88 kilogram. We do have the magnitude, but we don't have any direction. So this means that this is just a scalar. A woman skiing at the speed of 25 kilometers per hour. We do have the magnitude, but no direction, so this is scalar. We can also see that this one is a speed. Speed is the magnitude of velocity. The next one is a parachute falling at 20 kilometers per hour downward. you do have the magnitude and you also have the direction, so this one is a vector. The next one, acceleration due to gravity on Earth of 9.8 meter per square second, so this is the magnitude. Downward, the direction, so this is the velocity. This is the vector. The next one says number 5. We do have the magnitude but no direction, so this is the scalar. And the last one, your weight on a bathroom scale. Weight is a vector. It's your mass and the direction, which is going to be toward downward. So this is a vector. We can represent vectors in 3 different ways. One way is just words in words. For instance, I can say 5 kilometers at an angle of 30 degrees to the horizontal. This is just expressing a vector in words. I can represent 5 kilometers at an angle of 30 degrees to horizontal using diagram, or we call it geometric vector. For instance, I represent this example of 5 kilometers at an angle of 30 degrees to the horizontal. This is the geometric vector that I'm representing. And I'm going to denote the starting of the vector with A and the ending with B. I can also represent this vector using symbols as AB with a vector on top. So I can either represent a vector using words. I can say 5 kilometers at 30 degrees with the horizontal. I can represent it with a geometric vector like this one. Or I can use symbols like this one. These are 3 different ways that I'm using to represent the same vector. Now, the magnitude of a vector is represented with 2 vertical lines like this. This means the magnitude of vector AB is equal to 5. Now, the vector's direction, we can express it using different methods. The first one, which is very simple, is to use a graphical representation of the vector. For instance, in a case of the following vector AB, we represent the angle that it makes with the horizontal line. For instance, in this case, we can say 30 degrees counterclockwise with the horizontal, and the magnitude is 3 kilometers. So in this case, AB is a vector of the magnitude of 3 kilometers with an angle of 30 degrees counterclockwise with the horizontal line. That's the first way we can represent a vector. The next method for representing the vector's direction is called true bearing. Now, in a true bearing, which is a compass measurement, the angle is measured from north in a clockwise direction. So this is your north, and we always use clockwise direction, meaning this way. True bearings are expressed as 3-digit numbers, including the leading zeros. Now, in this representation, if we want to know north bearing, we are going to represent it with 3 zeros. Remember, in true bearing, we always reference northward direction as the main direction. So if we are talking about north, north is represented with 0, 0, 0, 3 zeros. East is going to be 0, 90 degrees. South is going to be 180 degrees. West is going to be 270 degrees. So this means that north can also be represented as 360 degrees. Now, if we have a vector like this one, AB or OB, and the angle is 40 degrees, I can represent it at 0, 40 degrees, which is 3 digits here, 0, 4, 0, in a clockwise direction. This is what we call a true bearing. The next method for showing the direction of a vector is quadrant bearing. In a quadrant bearing, our main line is north-south, and the angle is always between 0 and 90 degrees, east or west of north-south line. For instance, let's say we have north 23 degrees west. The first letter N represents the initial direction, so we are going north. Then it's 23 degrees going toward west. We know that west is to the left, so this means go 23 degrees to the west. So this is the angle, north 23 degrees west. For instance, if we have south 45 degrees east, this means that if this is north, this is south, this is east, this is west, then initially we are going south, so this direction, then 45 degrees east, so this means that we are going to go 45 degrees east of south. So this is going to be our vector representation, which is quadrant bearing. In quadrant bearing, again, we have 3 components. One, the initial direction of the travel, which is along north or south, which is this part. Then we are going to have our angle, which is here in this case 45 degrees, and then the ending direction, which is east. Again, we are going south, then we go 45 degrees toward east. So the direction is going to be with the vector OA, which is represented here. In the next example, we are supposed to describe each vector in words. The first one, which is A, we can say that it's 14 centimeter at 110 degrees with the horizon. The next one, which is B, since we are given the angle 135 degrees with north, I can use true bearing, and I can say 2.3 kilometers at a true bearing of 135 degrees. The next one, C, since we are given an angle of 35 degrees with south, I can use the quadrant bearing and I can say 9.8 Newton, and I can say south 35 degrees west. In the next example, we have to draw each one of these vectors and represent it with a geometric vector. For instance, the first one says vector v is 2 kilometers at the bearing of 020. So this means that if this is north, then 20 degrees clockwise, so it's going to be 20 here, and the magnitude is 2 kilometers. The next one says v is 4 kilometers again, so this is north. V is 4 kilometers at a bearing of 295. Remember that it's always clockwise in true bearing, and we always go from the north. So this is 90, 180, 270, and 295 is going to be somewhere around here. So it's going to be a vector of 4 kilometers, and this angle is 295. The next one says u is 30 kilometers per hour at a current quadrant bearing of north 40 degrees east. So this means that initially we are going north, so this way, and then we turn 40 degrees east, which is going to be to the right. So it's going to be this angle 40 degrees, and it's 30 kilometers per hour. The next example says u is 40 kilometers per hour at the quadrant bearing of south 70 degrees west. So again, this is our north, south, east, west. So north, south, east, west. So initially we are going towards south, so this way, and then we turn 70 degrees toward the west, which is going to be here. So this angle is 70 degrees, and the magnitude is 40 kilometers per hour. In the next example, we are supposed to write the true bearing of 150 degrees as a quadrant bearing. First of all, the true bearing of 150 degrees means the angle between the vector and the north direction is 150. The first quadrant is 90, then 180, so the vector is going to be something like this one. Now, we can either say that the quadrant bearing is north 150 degrees east, or we can say south. This angle becomes 30 degrees, so it's going to be south 30 degrees east. So either definitions here is going to represent the same vector. The next question says, write the current quadrant bearing north 50 degrees west as a true bearing. Again, it is north, so going this direction, and then 50 degrees west, so it's going to be this direction. So this direction angle is 50. To represent this one as a true bearing, we know that we have to represent the angle with the north direction, which is going to be this angle. If this one is 50, then it means that this angle is 360 minus 50, which is 310. So it's going to be 310 degrees true bearing. We are not going to define parallel vectors. Parallel vectors. These are the vectors that they have the same or opposite direction, but the magnitude does not necessarily they have to be equal. So if the vector AB is this one, a parallel vector to AB is, it can be a vector like, let's say, vector V this way, or a vector V this way. The magnitudes are not the same, but the directions are parallel to each other, either in the same direction or in opposite direction. How we represent two parallel vectors, we say AB is parallel to V. We represent them with two vertical lines. We define two equivalent vectors as two vectors that they have the same magnitude and the same direction. The location of the vectors is not important. For instance, if AB is this vector and V is this vector, as long as the magnitudes are the same, meaning the same length vector, and the direction is also the same, then we call these two vectors AB and V to be equivalent. So again, equivalent vectors are parallel vectors but with same magnitude and also the same direction. We defined opposite vectors to be two vectors that they have the same magnitude but opposite directions. For instance, if vector V is this way, the opposite vector to V is going to be another vector U, which is going to be in opposite direction but the same magnitude. The location of the vectors is not important. As you can see, V and U, they have different locations, but they have the same magnitude and opposite directions. Now, how we represent opposite vectors, we can say that V is equal to negative U. This negative causes vector U to change direction, which becomes like this, which means that U, V, and this vector here now, they are going to be equivalent. In the next example, we have vector AB, which is shown here. We have to draw a vector equivalent to AB and label it EF. So a vector equivalent, remember equivalent, they are parallel, they are having the same magnitude, but the location doesn't matter. So I can say that EF can be something like this vector that I drew. Write an expression to show how AB and EF are related. I can say that AB is equal to EF. The next question says, draw a vector opposite to AB labeled GH. So opposite to AB is going to be another vector which is going to have the same magnitude as AB but in opposite direction. So this is going to be GH. And how we can write an expression which shows the relationship between AB and GH, we can say that AB is equal to negative GH.